I'm not going to use y of t after all. I think I want to just use f of t, because I don't want you to think that we're always talking about y. Okay, this could be any phenomenon. So the idea is to create an equation where you give me a time, I'll plug it into this, and then I'll tell you the output. So for example, it might be something moving up and down. So you tell me the time, and I'll tell you the y value. So maybe it is a y. Or maybe it's something moving sideways, like this, and then you give me the time, and I'll tell you where it is horizontally. That would be like giving you the x, see? Or maybe it's something bobbing up and down, you know, or swinging back and forth, or going around in a circle. The point is, we don't have to think of this as y. It can be y, or x, or height, or whatever. Okay? T is time for the problems I've chosen. Okay? In some phenomena, t is not time. T might mean something else. T might be the position, the amount of stretch in your spring, or some other thing, or the amount of energy, whatever. But for us, t will be time, and f will just be position. Okay, so I'm going to write that down. For our problems. And t is time. But aside from the fact that it says t instead of x, this looks just like what I gave you yesterday. Right? Amplitude is still the absolute value of a. Period is still 2 pi over omega. Right? When we do our final answers for our models, we're going to write them in this form so that the omega is more factored out looking. So just go and write final answers. This is what I'd like your final answers to look like. There's a couple reasons why I like that form better than the form at the top of the board. I'll explain them later. So let's get started on the rules here. So what are the rules for creating your own function in a situation? Okay, first of all, you need the amplitude. So you can get the amplitude by taking the largest output value minus the smallest output value, all divided by 2. Okay, so I want you to think of y as output, not necessarily a y value, okay? It's position, because it could be an x value. It could be a horizontal position. But it's the change in position divided by 2. And then it's going to be, for vertical shift, largest y value plus smallest y value over 2. So those two formulas are very, very similar. This gives us amplitude. This gives us b, the vertical shift. Okay, now you're looking at this, and you might think omega is 2 pi over period. I thought period was 2 pi over omega. Period is 2 pi over omega. That's an awesome formula to use if you know omega. Okay? But if you don't know what omega is, if you're trying to create the function, you might know what the period is instead. So what this is on the right is the cross-multiplied version of this. I just trade period and omega like this diagonally. I guess it's this version. The reason we use this one on the right more often is because in real life, it's really easy to figure out the period of motion for an object. For example, when I push my son Timmy on the swing, I seem to have to push him about every 1.5 seconds. So I push him, he goes across, and he comes back, and then I push him again. It usually takes about 1.5 seconds, okay, between pushes. That's the period. So it's much more likely in real life that I would know the period, 1.5, instead of the omega. So I use the period to get the omega. Okay, so it's a little backwards there. This last one is just saying that you're going to need phi eventually. But to get phi, you're going to have to do some work. You're going to have to basically write this model down. At this point in time, you'll already know a and b and omega. And you'll plug in a t and a y value. One t value and one y value to get the last missing piece, phi. Okay, so let's just jump in and try an example. So my first one is about a buoy in the water bouncing up and down, and my second example is about a man swinging on a vine or a rope back and forth. Either way, they're repetitive periodic motion. Okay, so in this first example, we're out on the deep blue sea. There is a boat, let's say right here. Okay? There's a person in the boat, looking over the edge, and he's got a ruler in his hand. I guess it's kind of a long yardstick. That was a bit too long for a yardstick. Okay, so he's got a yardstick in his hand. Okay, yardsticks are typically the same. They basically have 36-inch mark at the top, and they have 0-inch mark at the bottom. Most yardsticks are pretty much the same, right? He's holding it up next to a buoy that's going up and down, up and down. So I'm just going to draw the buoy like this, if you don't mind. The buoy is doing an up and down bobbing motion. Those are inch symbols, not equal signs. I think I'll erase those. Okay, so it's going up and down, up and down. He sets a stopwatch. He starts it, and it takes him a second to look at the ball, the buoy. And he starts it, and he looks, and he notices at t equals 1, the buoy is right at the top of its motion. Okay, so at t equals 1, it says right here, it reaches its highest value on the yardstick, 24 inches. Okay, so y is 24 inches at that instant. Now, a couple things are implied here. They're not stated, but if the buoy is at its highest point, 24, then that means it will never go above that, obviously. So once it's reached that 24 mark, it's ready to fall back down. Okay? So it never reaches the 36. It never makes it to 25, see? Okay, so that's the topmost position on the ruler. And then he notices at t equals 3, it says right here, it is at its lowest value on the yardstick, 10-inch mark. So the lowest it ever reaches on this yardstick is the 10-inch mark. So all of its motion happens between the 10 and the 24. It goes back and forth. And assuming no outside forces come along, and assuming there's no friction of any kind or drag, the ball or the buoy will just do this forever. From 10 to 24, back to 10, to 24, to back to 10. And this goes on forever. Okay. So all of our models are hypothetical in one sense. We know that other forces will come into play, but we still can write the model as an approximate equation of motion. Okay, so what do I want to do? I want to follow the rules on the previous page. You guys have them at the top of the page. How do I find amplitude? Tell me. Largest y minus smallest y, and then don't I have to divide by 2? Yeah. Okay, well that's simple enough. That's just 24 minus 10 divided by 2. So that's 7. All right, getting there. Next is we have to find the b value. That's the vertical shift. That's just 24 plus 10 over 2, which is 17. And then we have to find omega. Omega is 2 pi over the period. Is that right? I think that's right. Okay. This is one part you might need to think about a little bit. Okay? So let's think for a second. What is a period? A period is when an object, or the amount of time that is required for an object to begin to recycle its motion. So we know that at t equals 1 is at the top of the ruler, the highest it can go. And then at t equals 3, it's at the bottom of the ruler. So we need to actually know how long it takes to go from the top to the bottom, back to the top. How long would that take? To go from the top to the bottom, back to the top.
2 seconds.
It's 2 seconds to get from the top to the bottom, right? To get from 24 to 10, it's 2 seconds. So to get back to the top, it's another 2 seconds. So altogether, it takes 4 seconds for the ball to go from the highest to the lowest and then back to the highest point. Okay, so you do have to think a little bit about your period when you're reading it. Okay, it's not stated the period is pi over 2, but that's exactly what our period is. I'm sorry, it's not stating that our omega is pi over 2, but that's exactly what it is. Okay, so we have to think about the period. A little bit harder than getting the A and the B figured out. Now let's go on to find the last missing piece, the phi. Okay, this is kind of the hardest part, and sometimes you'll need a calculator for it, unless you know your unit circle super well. Okay, so I'm going to write down the model the way I think it should go. So it's y equals amplitude times sine of omega t minus phi, don't know that yet, plus b. This is the best I can do right now. I don't know phi yet. Okay, in order to get phi, we need to plug in a y value and a t value so that phi is the only missing thing in this equation. So we get to go up here and look at the different y's and t's for the problem. Okay? So you can pick 1 and 24 for t and y, or you can pick 3 and 10 for t and y, but let's all agree together to always pick the smallest possible y value. Okay, so let's use the 3 and the 10. The book suggests the same thing. This way we'll all get the same answer in the end. Okay, all of our models will look alike. Okay, so let's use 10 for y and 3 for t. Okay, so I'm going to put 10 on the left. And for t, I'm going to plug in 3. I'm supposed to isolate phi now. And I think this is the first time, I know in my class, the first time you've ever tried to isolate something from inside of a trig function, but it may be the first time you've ever done it. Okay, so first thing I got to do is get rid of that 17. So that I can just subtract. And this gives me negative 7 equals 7 sine of 3 pi over 2 minus phi. Divide by 7. Dividing by 7, so I have negative 1 equals sine of 3 pi over 2 minus phi. What do I do now? I have to get rid of the sine. Okay, so this is what that inverse button is for. Okay, so you're going to use the inverse sine button for the first time in this class. And make sure your calculator is in radian mode. Why? Why is it so important? Because that 3 pi over 2 is a radian measure. Is it not? That's not in degrees. Okay, so we have to be very careful. Get that calculator in radian mode and type sine inverse negative 1. Okay, now, what does it give us? Negative 1.57, yada yada. $1.57. Gosh, that sounds familiar. 1.57. Where have I seen that before? Isn't that half of pi? This is exactly half of pi. This is negative pi over 2. Some of your calculators are sophisticated enough to actually write that. They won't say negative 1.57, they'll say negative pi over 2, but that's like the TI-89s and the more advanced machines. So what did the calculator just do? Let's talk for a second about the calculator. What is it doing there? What it's doing is it's trying to find an angle on the unit circle where sine is negative 1. See? So to the calculator, this means sine is negative 1. Now, what's the angle? So the calculator is looking around the unit circle and finding, oh, right here, the sine is negative 1. And it's saying that's at negative 90, see? At the bottom of the circle. This point is sometimes referred to as 270, but whenever we use the inverse button, we call it negative 90. Okay, so this is just negative pi over 2. That's what the calculator is doing there. It's trying to find that angle for you. Okay, but let's keep moving on. Let's continue to solve for phi. Subtract 3 pi over 2 from both sides. And we end up getting negative 2 pi equals negative phi. In other words, phi is 2 pi. That was the last missing piece for our model, and it's usually the hardest thing to get. But we're ready now to write our model completely. Okay, so here's the model in black. Y is equal to 7 times the sine of pi over 2 times t minus 2 pi all plus 17. We got everything we needed. And remember, I had asked you to write your final answer with the omega factored out. So we're going to actually write it like this. 7 sine of pi over 2 times t minus 4 plus 17. All right. That's your model. Let's say you're not sure you trust your model. I've been in that situation so many times. I've written it out and I think it's right, but I'd really like to know for sure. Try plugging in t equals 0. You should get what the problem told you, 24. Remember the time, when the time was, I'm sorry, try plugging in 1 is what I meant to say. Plug in t equals 1 and you'll see that the position is 24, just like the problem says. And then try plugging in t equals 3 and the position will be 10, just like the instruction says, see? And that's all very, very rewarding when you start plugging in the givens and your model is working. It's beautiful. Okay, so there's your model. There are many other ways to write this model, okay? But I'm just going to leave it because I don't want to use too much time explaining other ways to simplify it. Okay, on the next problem, after we write our model, we're going to start using it, okay? First, we've got to write the model. Okay, this is a problem about a man swinging alternately, over land and water from a rope that's hanging from a tree that is 10 feet from the waterfront. At t equals 0, he starts swinging from a platform 22 feet from the tree on land. And 2 seconds later, he is passing the tree for the first time. Where is the man relative to the water's edge at t equals 11 seconds? And is the man moving towards the water or away from the water at t equals 11 seconds? And how many times has the man passed the tree at t equals 11 seconds? This is a fairly sophisticated problem. You cannot solve it without the model. So let's get the model going. Maybe we could draw a picture real quick. Okay, so let's draw a picture. We've got land and water. And where they meet, they're calling that the waterfront. So you could just think of this as the bank of the river, right? So this is the water's edge. This is the water edge. Okay, it says that 10 feet from the water's edge, there's a tree. We assume it's planted on the land. Okay, so here's the tree. 10 feet from the water's edge. All right. Supposedly there's a platform 22 feet from the tree. That's where he started his swinging. And it's on land, so it's not out there in the lake. It's over here. So he's got his, like a platform here. And this distance is 22. And starting to realize that if he swings, he's going to probably hit the ground. So I'm going to fix my drawing a little bit. Let's move this all down. I need a taller tree. Let's see here. How do I delete my tree? I will make my tree taller. That's a big tree. Okay, but this way, if the person's on a rope, swinging, he can swing freely back and forth without hitting the ground. Okay, so this is what his motion is going to look like. It's going to swing like this, and then he'll come back again. Or he might decide to let go and go splashing into the water. It all depends on his mood at the moment he reaches his leftmost point. Okay, one thing we know about this motion is when he leaves that platform, he's probably going to swing directly to the left and downward a bit, right? But he's going to end up going, as if there's no friction, he's going to end up going 22 feet out past the tree as well, because he started 22 feet before the tree. So he'll swing past the tree and keep going another 22 feet. Okay, so this distance is also 22 from here to the tree. which means he will end up going out over the water at most 12 feet. Hopefully it's nice and deep there. He can let go and go splashing in without getting hurt. Okay, this is the best I can do with the picture, but I needed it because this tells me what to draw for a number line. I'm going to draw a number line now. This will replace the picture with 0 in the middle, 22 on the right, and negative 22 on the left. The whole problem is about this number line. Forget the picture, forget the tree, forget the man. This is all about that number line. I would like to create a model where if you tell me the time, I'll just plug it in and tell you where on the green line he is. For example, you might plug in t equals 10, and out pops negative 12, and that tells me he's right about here. Then I go back to the picture and say, oh, he's slightly above the water. You know, or maybe you plug in t equals 5, and you get like answer like 19. That means he's really close to the platform at that instant. You see? So we're assuming he's kind of holding on to the rope and just going back and forth, back and forth. But it's really about that number line. Okay, so this is what I'm going to call the x-axis. I'm going to call this the x-axis. And now I'm going to try to write down the givens. It says right here, when time was 0, he started on the platform. So I need to write t equals 0 right here on my number line. This means that this is where all things began. Started on that platform, his position was 22. The next part of the sentence says 2 seconds later, so what time is that? T equals 2, right? He is passing the tree for the first time. So this is happening at t equals 2. So it's passing by the 0 mark at t equals 2. Can you tell me at what time he ended up at the far left? If time 0, he's at the platform, and time 2, he's at the tree, then when does he reach the negative 22 marker on this number line? What time? 2 seconds later, right? So at t equals 4, right? So at 0, he's at the platform. At 2, he's at the tree. At 4, he's out over the water. He decides not to let go and go back again. Can you tell me what time he arrives at the tree? 2 seconds later, yes. Can you tell me what time he arrives back at the platform? 8. Can you tell me the length of one period? 8 seconds. So the period is the time difference between any two consecutive reoccurrences. So like, he was there at time 0, he was there at time 8. That's an 8-second period. You can also see it over here. He's going to arrive back over here at time 12. Don't use this middle point to figure out your period. That won't help you. It would appear that the period is a 4-second period. It's not true. You want to look at the extreme value way out on the left or way out on the right and subtract those 2 times. So that is your period. Okay. All right, so I think we're ready to get going. Let's go ahead and find amplitude. Now, according to the instructions, we're supposed to use the largest y value and the smallest y value. There are no y values here, guys. Our time is our x, and our x is our y. Okay? Our output is position on the x-axis. So you have to be a little bit less literal with that y of t. So this is talking about the largest green number minus the smallest green number. So what are those? 22 minus negative 22. So in other words, the amplitude is 22. Well, yeah, that makes sense. He swings 22 feet on either side of the tree. Okay. B is your vertical shift. That's found by doing 22 plus negative 22 over 2. In other words, 0. This just means that his center of motion is the center of the number line. That's actually kind of nice. It's nice to have a 0 every now and then. Next is period. This is something we had to think about. Period is 8. That makes our omega 2 pi over 8. In other words, pi over 4. And we have 3 of our 4 ingredients for the model. Okay, so here's our model so far in black. y, which is really the x coordinate. So the x coordinate of his position as time goes on is a sine omega t minus phi plus b, which is fortunately 0. Okay, now we want to use one data point, a red and a green. We could choose any of the red-green pairs to substitute in for t and x of t. We had said that we were going to pick the smallest possible output value when we do this. So can we please all agree to use this point over here? Data 22 is the smallest screen number I have. So let's use the t equals 4 and position equals negative 22. So this has the smallest output value. Okay, so I'll put negative 22 equals 22 sine of pi over 4 times 4 minus phi. And our goal is to solve for phi. Just like last time. Let's divide by 22, and we get negative 1 equals sine of pi minus phi. We can do our inverse, or some people call it arc sine. But we did this earlier, and we learned that this is just negative 1.57, which we interpret to mean negative pi over 2. The calculator gave us that, but we believe it's negative pi over 2. And then we'll subtract the pi over, and we learn that phi is 3 pi over 2. If you have to go decimal, fine, do it. At least try to finish the problem. And if you think your model stinks, show me that it stinks. Plug in your times and show me that it's not working. But don't stop midway through your problem. Any scientist at least makes a hypothesis, right? At least do the hypothesis and write down what you think the model is. Okay, so now we know the full model. It's y equals 22 sine of pi over 4t minus 3 pi over 2. And I had asked us to factor out the omega. So it's 22 sine of pi over 4 times t minus 6. Final answer. And you guys remember what I told you was the really fun part? Plug in time 0 and show that he's on the platform. Plug in time, what did I say it was? Time 2, show that he's at the tree. It's really fun too, actually. It works out great. And this model, I tested it, it works. Let me just show you how to use your calculator to test it and to answer questions about it. Because we're going to talk about time 11 here. Okay, so take out your calculator. This is really the only part where you have to use calculator, really. And even that's debatable. But just go under y1 and just type the model. Okay? Don't use t, obviously. Use x. But y1 equals 22 sine of pi over 4 parentheses x minus 6. Just everybody punch that in real quick. We're going to try to talk about time 11. Okay? Okay, once you have this typed, click on window, second window. So it's called table set. Open this screen up. And put this thing on ask mode, right here. Just the independent variable. Yes, you can also open table setup. Oh, I thought you meant other models of TI calculators.
No.
Yes, there are an infinite number of models that work.
Oh, yeah.
Did you use a cosine?
No, I used sine, but somehow I got a different one, and I plugged in the two givens, and they worked.
Did you plug in the same given I used?
0 to 22. Yeah, I just, like, what you were drawing the picture, I wanted to see if I could...
You got ahead of it. Okay, so what you probably did was, when it came time for you to plug in a t and a y,
Yeah, I did
you might have
0.
chosen, you used this one, 2 and 0?
Yeah, I took 22 and 0.
Okay,
so.
it's fine. It's just our models are going to look different. So for the test, if you don't mind, use the smallest y value
Yeah, because I didn't realize
that's even
negative.
possible for the situation. That way we just all have the same answer. Okay. This is the kind of the funnest part, is using the model. Okay, we got that done. Now if you press table, yours will probably be blank here, like this, right? The cool thing is you can type in any x you want. So you can totally look at the motion. Watch this. At the 0th second, watch. There he is on the platform, 22. Beautiful. First second, he's at 15.556. At time 2, he's at the tree, 0, see? At time 3, it looks like he's out over the water a little bit. Remember, the water is at -12. You can just play around with that. Okay, that's kind of neat. That makes you really believe the model. Okay, but let's talk about time 11. So just type time 11. It says y equals -15.56. So let's go back to our picture. Remember, our picture had a tree, and we said we weren't too interested in the picture really. It was that number line. This represented positive 22 on the number line, and this represented negative 22 on the number line, the tree being in the middle at 0. So what would it mean for, maybe I should be using x instead of y for my model name. When I plugged in 11, it gave me -15.556. What does that mean? That is the exact location of the person, see? So the person is right about there. He's at -15.556. And we already said that the water started right here, only 10 feet from the tree. So he's basically 5.5 feet out over the water. So this is at -10. Remember the waterfront? Okay, so you could write it this way. The man is 5.556 feet out over the water. At t equals 11. Okay, but there's more we can do. Check this out. Now let's go to our table again. And let's see what happens just 1/10 of a second later. So let's put in 11.1. Where is he at now? -16.73. By the way, if these numbers aren't accurate enough for you, just put your cursor right on the number and you'll see it with more accuracy. Because on the AZ calculus test you need 3 digits after the decimal. So just put cursor right there, highlight that, you'll see it. Okay, so at 11.1 seconds, we know he's at -16.729. Well, that's just barely to the left of the point we just had. Just a foot over, you know. So I'm going to write a little sense about that. Since he is at since he is 6.629? Since he is 6.729 feet out over the water, since he is 6.729 feet out over the water at t equals 11.1, yeah, I think he's headed to the left, see? I can tell by these two positions that he's moving leftward at this instant, see? Okay. So my justification is what I just wrote, and then I can put, this means he is moving leftward. He is moving leftward at t equals 11 seconds. So without calculus, it's kind of hard to show the direction of motion, but I kind of used t equals 11 and t equals 11.1, and I saw that he had moved a foot to the left. So that means he's moving leftward, obviously. And the last question is, how many times has he passed the tree? Well, we actually know the exact times he passed the tree. Remember back in the picture? Going all the way back to the top here. Remember he passed the tree at time 2 seconds. he passed the tree later at time 6 seconds. Doesn't he pass the tree at time 10 seconds also? Okay, so I'll just write that. He has passed the tree 3 times. They are time 2, 6, and 10. You have a worksheet tonight. It's on Edmodo at 3 o'clock. It has 2 problems, but it'll take you 40 minutes. Try to follow exactly what I did. Okay? Probably 40 minutes. I don't know.